All right, so last term we finished up talking about aromaticity, and we went through a couple of reactions where we talked about reactivity at the benzylic position. Chapter 19 is closely related to chapter 18, but now we're actually going to do reactions on the benzene substituent itself. So let's take a look at a couple of examples. Let's say I have just plain old benzene, and I try to react it with bromine. What will happen? No reaction. A lot of people will look at this and they'll say, but there's a pi bond in there, right? We've seen addition of bromine across pi bonds before, but what's different? Yeah, it's aromatic and it's not a true double bond, exactly. So if we look at this and we tried to draw our addition product, we could try to draw it where we've got one bromine up, we've got another bromine down, plus it's an enantiomer. However, in this case, we've got broken aromaticity. You could try to do this, but thermodynamically, it's an uphill reaction. It's non-spontaneous. It just won't occur. However, there's another odd thing with this reaction. And this was found when you add iron, that you can actually get one bromine atom to attach directly to your benzene ring. It's a little bit odd, but one nice thing about this compared to the one on the top is that this is still aromatic. Why didn't I draw the bromine with a dash or a wedge? It's not a stereocenter. Remember, anything coming off of a benzene ring just draws a straight line. You don't have to include stereochemistry. So let's take a look at the mechanism. The mechanism for this reaction, I'm going to use just a generic electrophile. And this electrophile I'm going to write out as E+. So if we think about benzene, it does have pi bond character. Yeah. Benzene is a really weak nucleophile. If we're going to react this with an electrophile, that means our electrophile has to be super strong, right? And let's try to work through the arrow pushing with this. So we know one of these pi bonds can be nucleophilic. This pi bond can attack our electrophile. And I'll just pop this electrophile on there. There was also a hydrogen on that carbon, so I'll draw that in. And then over here we also have a hydrogen, but now we've formed a carbocation, right? So we're not quite at our product, but what do you think could happen next? It's not aromatic, right? An elimination reaction, right? This looks pretty similar to E1 elimination that we saw in the first term. And this is a really important intermediate. This is called a sigma complex. Or some people call it an uranium ion. And it's very, very unstable as a carbocation because it's not aromatic. However, if we have any sort of very, very weak base, this weak base can come, grab this proton, do an E1-like reaction, and all of a sudden we've installed our electrophile, and we've got a happy aromatic molecule. Does this make sense? Pretty straightforward. There's a lot of reactions that are all based off of this exact same mechanistic scheme. Just make sure that you remember to do the E1 type reaction. It's not unimolecular or anything like that. It actually goes through an intermediate of this sigma complex. So let's take a look at halogenation reactions. Is it okay if I leave this page? 1 second. All right. The first and most important reaction is halogenation. And typically with halogenation, we see it done with bromine or chlorine. You occasionally see it done with iodine, but you don't really see it done with fluorine that often. So with bromine, we said we add Br2, and then what was the metal we use? Iron. And specifically, we use iron tribromide, and I'll come back to this in a second. I'll just put a little asterisk there. And if we do this, we can install bromine directly onto our benzene ring. If we want to install chlorine,
Wait, Professor.
Yep.
What is that little stars thing?
It's an asterisk. I'm going to show how we make the boron or the iron tribromide. If we want to do chlorination, we do Cl2 and aluminum trichloride, so chlorine gas and aluminum. And if we do this, we can get the analogous reaction with a chlorine atom. What can we do if we install a halogen onto a benzene? How can we make the benzene into a nucleophile? Grignards, right? So now we've got access to turning a benzene ring into a Grignard reagent. There's also a huge swath of organic chemistry called organometallic chemistry, where these are used in coupling reactions. Our book doesn't really hit on them too heavily, but these are very, very important intermediates in organic chemistry. Let's go back to the iron tribromide, though. To make iron tribromide, it's pretty easy. All you do is you take 2 equivalents of iron metal, 3 equivalents of bromine, and you'll make 2 equivalents of iron tribromide. What happened to the iron in this reaction? Was it oxidized, reduced? It was oxidized, right? Elemental iron was iron 0. Iron tribromide, we go to iron with the positive 3 charge, so we're just oxidizing the iron and forming iron tribromide. So oftentimes you'll see it written out as just Fe. Other times you'll actually see it written out as FeBr3. You can write it either way. I'm fine with that.
The aluminum chloride forms the same way?
Typically you actually buy the iron tribromide and aluminum trichloride. Let's go over the bromination mechanism. All right, so if we look at bromine, I'm going to go old school and draw in all of our lone pairs. Bromine is a relatively decent electrophile, right? We saw in chapter 9 that alkenes can attack bromine, so the alkene was our nucleophile, bromine was our electrophile, but it's not good enough in this reaction. So I'll just write, it's a weak electrophile. However, when we react this with iron tribromide, we have a unique reaction. What else am I missing in this iron tribromide if we're thinking about the orbital picture? What do you guys think? Yeah, p orbital, right? So iron tribromide has this p orbital sticking up and down. We've got a lone pair. We've got an empty p orbital. This is Lewis acid-base chemistry, right? So you remember in Lewis acid-base chemistry, we said that a lone pair can be donated into an empty p orbital and you form a Lewis acid-base adduct. This is exactly what's occurring here. Which one's going to be our acid? The iron complex or the bromine? The iron complex. The thing accepting electrons will always be your Lewis acid. And so if we go through, we've now formed something that looks kind of odd. This iron now has a negative charge, and this bromine now has a positive charge. If we think about this, there's a super strong dipole right now between these two bromines, and this makes this a very strong electrophile. So now if we take some sort of benzene or benzene derivative, I'm just going to draw it in right here. This can actually reach up, attack that super polarized bromine, and then pop these electrons over to the bromine with the positive charge. And now we've got, let me draw it over here. Got this tetrahedral iron complex now. And this iron is still a negative charge, so it's not super happy. So we've formed our sigma complex, but we don't have aromaticity yet, and we don't really have a base yet. So this next reaction looks a little bit weird.
Can you just go out a bit?
Yeah. In the next reaction, we're going to actually use the iron complex as a base. So this bromine will come over, grab this proton, clamp down, and will restore aromaticity to the molecule. So let's add in our new arrows. If you notice, we regenerated our catalyst so that iron tribromide was recreated, and then our byproduct is going to be HBr. So we've created some acid. We normally don't think of bromine or bromide as being a very good base, but why is it acting as a base in this reaction? Anybody have a educated opinion or guess? We know HBr is a super strong acid, so why would the bromine in this case want to grab that proton?
Maybe the other one's weaker. Never mind. I'm not sure.
Well, let's look at it, right? This is not aromatic. Which means it's not only unhappy in terms of Huckel's rule, but it's also a carbocation. Down here, we've made this aromatic, and it's no longer a carbocation. So sometimes we get stuck in this mindset of thinking of strong acids, strong bases, but we also have to consider the other components in the reaction. So in this case, bromine will actually be a decent enough base to do this deprotonation, simply because we're reforming an aromatic ring. Does that make sense? All right.
So which part of the iron tetrabromide is attacking or is grabbing the proton?
Typically, when you see this arrow done, you see the arrow starting from this bond. So it's the bromine and the electrons from that bond. So it's essentially Br minus going in and attacking. And when you do that, the iron loses its negative charge and becomes neutral. Make sense? You guys are super quiet. You're thinking about how nice spring break was. Let's look at the chlorination mechanism. The chlorination mechanism is also very, very similar, except this time we've got chlorine gas instead of bromine. And what was the metal that we used this time? Aluminum. So we've got aluminum trichloride. It's a very, very good Lewis acid. So if we look at this, the chlorine is going to donate its electrons into this p orbital, just like we saw in the previous reaction. The aluminum becomes negative, this chlorine becomes positive, and we form a super strong dipole. Just like before, we're going to have this react with a benzene or benzene derivative. So this benzene will reach up, grab superpolarized chlorine, pop electron density over to the neighboring chlorine. And then we've got the aluminum complex. What do you think the next step is?
Attacks H.
Yeah, it's completely analogous to the bromine reaction. So it's something that oftentimes people overthink because it's a new reagent. But one of these chlorides will come, attack that proton, restore aromaticity, and all of a sudden we've regenerated our aromatic ring system. We've got aluminum trichloride remade, and our byproduct for this reaction is going to be HCl.
So do you draw a negative charge for the iron one? Oh.
Yep.
Okay.
So the question is, if we wanted to do iodination, what sort of reagents would we use? Would I2 work? Not quite. In fact, there are some reagents that will create what's known as I+ in solution. And in that case, I+ is a very, very strong electrophile, and you can actually get aromatic iodination. However, it's not even presented in the Klein textbook because it uses some odd reagents. I just wanted to let you guys know that it exists. Why don't we see fluorination? Yeah, it's way, way too reactive. Fluorine chemistry is very dangerous. I'm sure people have tried and unsuccessfully blown up apparatus and whatnot. Let's go to sulfonation next. So we've done all the halogenation reactions. Sulfonation is really similar to halogenation. And in this case, what we're going to do is take a benzene system. Oop. This will be locked out. And we're going to add fuming sulfuric acid. And if we add fuming sulfuric acid to a benzene derivative, we can get a sulfonate functional group attached onto our benzene ring. Does anybody know what fuming sulfuric acid is? A lot of people think it means hot sulfuric acid, not quite. Fuming sulfuric acid actually means that it has gas dissolved in it. So let me write this down. It has sulfur trioxide.
Sulfuric acid.
Yep, so H2SO4 is sulfuric acid. Fuming sulfuric, oh, I forgot my R. Thank you. Fuming sulfuric acid has sulfur trioxide added. So if we look at sulfur trioxide, it looks kind of funky because sulfur doesn't obey the octet rule in the way that we're normally taught. And the weird thing with sulfur trioxide is that the sulfur oxygen bond that's shown is equivalent to a sulfur oxygen single bond, where the sulfur is positive and this oxygen is negative, right? So if we think about sulfur trioxide, is it a good electrophile? Yeah, definitely. That sulfur has mostly positive character. So if we think about the sulfur, if it's got mostly positive character, that means the sulfur is going to be a super good electrophilic site. Oops. All right, so let's take a look at the mechanism for this.
And is the sulfur trioxide a gas?
Yeah, so what they do is they essentially bubble it into the sulfuric acid, and just like a bottle of soda, some of that gas will dissolve in the sulfuric acid. It's pretty nasty stuff. You have to order it, and it takes usually a month to arrive because they have to transport it using very special containers. They won't ship it to you on an airplane. All right, let's take a look at the mechanism. The mechanism primarily involves the sulfur trioxide. The sulfuric acid is more or less a solvent. So if we try to do our arrow pushing, we know benzene is going to be a weak nucleophile. We know sulfur trioxide is a very good electrophile. So if we draw our nucleophile attacking our electrophile, we're almost there. But sulfur doesn't want that many bonds, so we're going to pop this set of electrons over here. So now we've got our rhenium complex. The weird thing in this reaction is that sulfuric acid, or the conjugate base of sulfuric acid, will actually act as a weak base. So this super duper weak base is strong enough to grab this proton, clamp down, and restore aromaticity. We've also created sulfuric acid, or reprotonated it at least, in this step. So what do you think will happen next? Yeah, just protonation of that oxygen. Oh, let me move this down a bit. And there we go. We've installed a sulfonate group onto a benzene derivative. This is pretty common in drug chemistry. These allow compounds to be nice and water soluble. However, one kind of odd trick is you can go directly back to this benzene by doing this under dilute conditions. Let me zoom out on this. If you take dilute sulfuric acid, you can actually pop off that sulfonate group.
Will the mechanism the same?
No, we're actually not going to go into this mechanism too much, but what this is really useful for is people will install sulfonate groups as a blocking group to occupy a certain position on a benzene ring, and then later on when they're done, they pop it off. So it's kind of like a protecting group in that aspect. Does that make sense? I know we're covering a lot of reactions on the first day. I think we'll just do one more and we'll call it good. The next reaction we're going to look at is nitration. Nitration's pretty similar. This time we take nitric acid and sulfuric acid. And if we do this, we can actually add a nitro group onto our benzene ring. So let's take a look at a cool example of this. What's this compound called? Toluene, right? So if you take toluene and you react it with nitric acid and sulfuric acid, you'll add on some nitro groups. Oops. There you go. So we've got this methyl group here. We'll get one nitro group installed on the opposite side of the ring. Is that ortho, meta, or para? Para. And then we'll also get a nitro group installed here. Is that ortho, meta, or para to the methyl group? Ortho.
Oh.
So if we were to name this, what would it be called? This was an example I gave last term. It's be 2, 4, 6. Trinitrotoluene, also known as TNT. This isn't a reaction I recommend trying at home. An explosion is the worst that can happen. Let's take a look at the mechanism for this. Yeah, if you are interested in explosives chemistry, not that you should be for a hobby, the more nitro groups you install on a compound, the more explosive things tend to become, because nitro groups really, really want to form nitrogen gas and oxygen gas, right? They aren't happy on a benzene ring. So if you look at the majority of explosive compounds used in the military, most of them have a lot of nitro groups on them. Let's take a look at nitric acid. So with nitric acid, I'm going to draw in all the lone pairs just for fun. This oxygen has a negative charge, and this nitrogen has a positive charge. So nitric acid is actually a Zwitter ion. And when we react this with sulfuric acid, not quite. You guys are actually going to do this in lab in a week, so I hope it doesn't go boom.
Wait, Professor, you say if the in a compound it has a positive and negative, it's very unlikely to form?
It can happen. A positive right next to a negative on a molecule is called a Zwitter ion, and they happen because of resonance, right? That negative charge is actually delocalized across both oxygens, right?
So you mean the oxygen probably forms some structure delocalized?
So if you were to delocalize this, you could pop up that electron density onto that oxygen. So in this case, it is stable. Normally, we don't like seeing molecules with multiple charges, but this is a weird exception. So what's a stronger acid, nitric acid or sulfuric acid? Sulfuric acid is kind of the benchmark for strong acids. So this will actually get protonated by sulfuric acid. Oops, sorry, wrong arrow. I'm ruining everybody's notes. There we go. So we're going to protonate this oxygen. And I'll show you why in a second here. So this molecule looks super unhappy. Oops, that should be a plus. Thank you. There we go. So we've got protonated nitric acid. This is a super unhappy looking molecule. However, we've got water on there that can act as a good leaving group, right? So this negative charge, whoops, will actually pop down and kick off our water as a leaving group. When we do this, we form this funky looking molecule.
Wait, you got OH2 there, but what about the top one?
So this is our leaving group. So when that oxygen donates electrons down, it becomes a new double bond between oxygen and nitrogen, and water is kicked off as a leaving group.
You're doing the last one, sorry.
So if we look at this, this is called a nitrosonium ion. And this nitrosonium ion is a really, really good electrophile, right? Because that nitrogen has a positive charge on it. So if we take benzene, I'm just going to draw benzene above our arrow. This benzene will attack this electrophilic nitrogen and then kick up electron density onto this oxygen. We're almost done. We've got our rhenium ion right now. What do you think the next step will be? Elimination, right? So the question is, what do you think is going to be a better base? We've got water around in solution, and we've also got the conjugate base of sulfuric acid. What will be the better base? Definitely water. So in this case, the sulfuric acid does nothing more than protonate your nitric acid. The water is what drives the reformation of your...
Why is water better?
Sulfuric acid's a super strong acid, which means its conjugate base is incredibly stable, where water can act as a weak acid or a weak base. So when we do this, we reform our aromatic ring, and we get our nitro group installed. So nitro groups are used extensively in organic synthesis. Yeah. And there's also one cool deviation that you can use with the nitro group. You can convert a nitro group into an amine really, really easily. So that's going to be the reaction we're going to finish up with today. So if we take nitrobenzene, we can convert this into an amine. And what's this compound called on the right? Aniline, right? So we've gone from nitrobenzene to aniline, and in order to do this, all we need is acid like HCl, and we can use iron or zinc. So this is a very important reaction, and it's one of the main ways for converting a nitro group to an aniline. Sound good?
Do we need to know the mechanism for that?
No. Yeah, this is one of the weird organometallic ones that I'm not going to expect you to know. All right, so remember your problem of the day is due tomorrow. Try to get started on sapling sooner rather than later because you can already knock out a good chunk of the sapling problems.